Okay, hi. I'm here to talk about Python, pyramid and embedded devices. My name's Justin Clacherty. I'm from Redfish Group, as Ed's already said. We're a small product design firm in Brisbane, and when we're not working on our clients' work, we've been developing AWP1, which is an open router project, an open hardware, open software router. And we're using Python and Pyramid for the web interface on that. So today I'm here to talk to you about embedded devices and what we can do to improve the human interfaces to them. Try and be kind, this is my first time talking at a conference. Okay, so embedded devices. Are there any embedded developers in the room? A couple, excellent. Okay, so for everyone else, embedded devices, they're basically just computerized devices that aren't servers or desktop machines, computers. They're things such as your printer, a phone, tablet, navigation systems, home and building automation systems, Raspberry Pi, I'm sure some of you have heard of that at least. Network appliances, so routers, consumer NAS devices. Basically, they're things that have been developed with a specific purpose in mind. There's a few criteria which most embedded devices fit, and it can cause a problem for things like running Python on them. Basically, they generally have fairly slow CPUs, though that's changing. Much of this is changing. Relatively low amount of memory on them. Low storage, you're talking sometimes K, sometimes megabytes, rarely gigabytes. But yeah, as I said, this is changing. Larger systems are starting to come out with faster processors. So what's the problem? More and more internet devices, embedded devices, are becoming internet enabled. So we've got the Internet of Things. It typically means that there's going to be a web interface on these devices, and that's used for configuration and management of the devices. So what's the problem with this? Well, I don't know if you've looked at your routers recently or any other devices, but they're just awful. These aren't the worst ones I've found, it's just that some of the really bad ones, I know the people who've developed them, so I didn't feel it was nice to put them on display here. So, why? Why are they so bad? Well, primarily it's because engineers develop them. Designed by engineer on a user interface is not good. But that's not the only problem, that's just being a bit flippant, I think. Really, it's because they're typically developed on fairly tight budgets. A lot of the smaller embedded devices out there, industrial devices and things like that, are typically being designed by very small firms. So they don't have a lot of resources to spend on things like user interfaces. And previously, they haven't really had to worry about it. The other thing is that the type of people who are coding on this, they're much more interested in getting into the raw functionality of whatever device they're creating. They're not so interested in people, and so they don't really care so much about how those people configure and use the device. It's much more fun working on the rest of it anyway. Also, configuration and management systems are typically left to the last minute, partly for that reason. They're developed on systems with minimal resources. You don't really have a lot of code space, RAM, CPU space to deal with user interfaces, which can be quite large. But as I said, that's changing. And when you do get around to doing that, the amount of work that's involved in building those back-end systems to actually serve web pages and deal with all the checking of user interactions, making sure no one's putting in the wrong text, items, whatever. That actually takes a fair bit of code. And these guys are writing in C and C++. And there's quite a lot of effort involved in writing that base of code that you need. And there's not really huge numbers of frameworks around to use on there. There's a few, but not a lot. And what that means is that because good UX design is iterative, you just can't go and write that base code, test it, find that someone wants to put this widget here, or the slight functionality of that widget might change, and easily change it, because the code's just not that simple. One of the other problems is a lot of these companies really don't value UX. They're in industrial systems, they're out at mines, they're in things like drag lines and shovels and trucks, and they're used to seeing ugly industrial systems. So the people are used to it, the companies don't care about it. And lastly, they're designed by engineers. So why does it actually matter? Well, the biggest problem is actually security. If you have a system that is difficult to use, difficult to find settings, difficult to navigate, people won't use it, people won't be able to configure it properly, and you end up with poorly configured devices which are insecure. And this is a huge problem with things like wireless routers and routers in general. A lot of people just pick it up, run with the little app wizard that it sometimes has, and that's the end of it. They don't care about all the things like setting different passwords, disabling WEP on a wireless system because it can be trivially bypassed. And the other problem is because they're typically left as the last minute thing, they're not tested particularly well, and they tend to have a lot of backdoors in them. Other problems are that from a sales perspective, people just won't buy your product. If your product's not easy to use, no one's going to want to buy it a second time. That's for the business people in the room that look at it and go, well, security, I don't care. Well, you'll care when people don't want to buy your thing, or your product's sitting up there on Slashdot or whatever tech site with people broadcasting that it's trivial to bypass everything in it. So what can we do? How do we overcome this? Well, Python can help here. As I said, embedded devices are typically low resources, but they're starting to not be. So you've got your Raspberry Pis out there, and the Raspberry Pi has, I think, 60 meg of RAM or something like that. So we're not talking about systems that have Ks of RAM and Ks of flash anymore. They're Linux-based, so you can put Python on it fairly easily. You now have tens to hundreds of megs of RAM on the things, large flash storage. CPUs, still not so fast, but they do range up to the gigahertz range. Smaller systems like your typical routers are probably only going to be 100 to 200 megahertz. But in applications like that, you're not really going to have so many problems. It's not like people are going to be consistently logged into them and using it as a web application constantly. It's a configure it once, and every now and then you'll go to check on it for some diagnostics. So, once again, good UX is an iterative process. So if we use Python, there's an awful lot of frameworks available. You've already got that base code. You can pull in lots of different modules to do most of the stuff you need. You can pull in web frameworks, which are going to be able to help you out. And you don't need to spend that ridiculous amount of time just building a web server in C or C++ before you can even start looking at the user interface side of it. So this is really going to help. Now, there still are going to be some systems that won't be able to support something like Python. But even in that case, you can still use it. So you can go and develop a Python web app, and you can use that for your user interface development and go through that iterative process. At the end, you'll have a decent interface in front of you. People will be able to use it, and you can use that as a base to then go and build something that's smaller in whatever language you're choosing to do. There's also instances where people don't really want to put something that's compiled on the machine, or whether the source code is effectively available on their system. So they're going to want a proprietary binary to put on their system. But if you can quickly go through that iterative process and actually work out what you're going to do on the system, then it's a much smaller task for the guys to come in and then go, okay, well, this is what you want. We can develop the base code for that. All the front end work, so the JavaScript, CSS and whatnot, is just going to come straight across. You can fairly easily write templating systems that'll match whatever templating system you decide to use under Python. So there's a few challenges to look out for. Okay, so the first challenge will be your embedded developer. They'll basically laugh at you hysterically when you say you want to put Python on their system. So once they've finished that and told you that it's going to use too much memory, too much CPU, too much storage, which it does, well, you tell them it doesn't have to. So here's what you need to do. Storage. Embedded devices don't have much storage. What storage they have is typically not writable. So that means that you can't have pip on there or easy install. So if you're missing a module, it's not trivial to just install it. There's no editing of files on the device, so during development you can't just go in and edit your Python file to get things up and running. There's a bit of rigmarole that you have to go through to do it. But there's ways around this. Easiest is do the development on a PC. Now, that seems obvious, but it can lead to some inconsistencies. Not all Python is the same. So once you pull it across to your embedded device, it may not work perfectly. So you need to make sure that you're testing on the device as well. So sure, develop on the PC, but regularly test on the device, assuming you have it, because software dev typically starts before you have hardware available. Another option, if it's a Linux system and you have enough memory, is just run a tempfs system. So basically running a file system in memory, and then you can work in that, or NFS to network attached storage on the systems. So there's a few ways around it. The next thing is memory. Memory. It uses a lot of memory. Anyone who tells you Python doesn't is not really an embedded developer and doesn't understand what a lot of memory is. So, once again, there's ways around it. Python is modular. It can be compiled modularly. So you can pull down the size of it. You can pull down the storage size of it. You can pull down the amount of memory it's going to use. There are a few embedded flavors of Python out there. You don't have to use CPython. You need to make sure that you're strict with memory allocation and deallocation. Profile. Make sure you profile everything. Understand what your code's doing. Understand what the impact of things you are doing will be. And profiling is the easiest way to do that. Also, obviously, understanding the language further. Python has a lot of built-in ways of doing things which can help you. Use them. So you've got generator expressions. Use those rather than storing large amounts of data in memory. Use the correct containers for the data types that you have. So tuples for immutable lists, Python arrays for arrays of numbers. Essentially act like you would if you were writing embedded code in C or C++. C++ was something that a lot of people shied away from for embedded code for a long time. Some still do. And it was basically because there's a lot of people there that just don't understand what the implications of using certain features are. You don't have to use them all. So use what's suitable for your system, your software system, and your hardware system. Speed is the other problem. We're still running on fairly low speed CPUs, as I said. So while they've gotten faster, they're not desktops. Python's great though. It allows you to really easily implement C and C++ libraries that you can link into. So, profile. I'm sure we've got profiling in there again. Yes. Profile, profile, profile. If there's something that is taking up too much time, look at it. Can it be moved to another language, something that's going to run a little bit quicker? If it can, do it. Threading on embedded systems, you're typically going to have single CPUs, single cores. So you need to think about that, and asynchronous I/O is typically the way to go. So use greenlets and gevent. That'll make things a lot easier for you. There are a few embedded systems out there that have multiple cores in it, but still, you want to do the best you can, so use those. Profiling again, yes, know what your system is doing. And a lesson, polling can be evil. Now that's to do with, we have a client who asked us to write a web interface to some data systems that they had. We had to do it in a bit of a hurry for them. We wrote all that, it works, it's fine, it runs on servers and desktops. Really, it would be nice for these guys to be able to put it onto an embedded system, so when they're selling their product to smaller clients, it's in the transport industry. So when they're selling it to smaller clients, they can just give an appliance server rather than having to go and tell these small clients, oh, you need to buy a server with these specs and you need to then install Windows or Linux or whatever you're installing. So embedded systems would be great, but what they ask for won't actually work. And that's because the dashboard they have has 3 tables in it, which are polled every 5 seconds or so. One of those tables has about 100 columns in it, which is sortable on a per user basis. Another one is just a list of alarms or events that come through. And another one is just a counter of alarms so that it can notify people and set off noises and whatnot to alert people that something's going on. Now, this is fine on a server, but when you're running on an embedded device, I think it took up about 25% CPU usage when one person was looking on it on the dashboard on a gigahertz CPU. So that's obviously not going to scale very well. 4 people, your system doesn't work anymore. So polling can be evil. Use WebSockets where appropriate. So code like that can fairly easily be rejigged so that you can do WebSockets, and the alarm stuff is all events, so that can just be sent out as needed. And even the polling of the main table in there can fairly easily be done with WebSockets. But that comes back to know your code. Now, the guys that had been working on this previously probably wouldn't even know that, okay, well, this is going to cause problems. But when they get 100 people on it, even on a server, it's going to cause issues because the CPU usage is, it's linear. So while it might be 25% on our little embedded device, it's 5% on the server. So that quickly gets up to 100% once you've got a lot of people in the system. Okay, And lastly, avoid large frameworks. I know the Django guys are here, and that's great, but it's not going to work on an embedded system. So Flask, Bottle, and Pyramid are reasonable for these things. Pyramid's fairly big, but for us, we've got more than enough resources to use it. And it's just a bit nicer because you can tailor it a little bit better to what you're doing. So for us, our application stack is we're using Nginx so that we can basically do HTTPS proxying. There's a G-event application server. That's so that we can easily tie into WebSockets. We've got a diagnostic section which shows network throughput and a few other little things, and that's just done via WebSockets. The Pyramid framework, we chose that basically because it just rolls authentication into it. We've used it before. You can choose your templating language. You just have a lot of options in how you configure it. And client side, we went with Patternfly, which is something Red Hat just came out with. They're trying to change the user interfaces in a lot of their systems so that the configuration is the same across different products. So we just felt, well, why not use theirs so people who are using Red Hat systems will understand it and more easily know what to do. We're probably not going to have time for a demo, are we? 4 minutes. Oh, yeah, okay. We'll try a quick one. So, a quick demo. Has anyone used Pyramid before? Oh, okay, so a few. That's cool. So, we'll do as much of this as we can in the time allotted. Basically, we'll create a virtual M environment. I'm sure most of you can do that. Create a standard Pyramid app. Then I'll just show you the rough layout of Pyramid and what we've done when we've plugged in some client-side information, so the Bootstrap, Patternfly system, and authentication. Okay, so I can't actually see what's going on here. Okay, great. Okay, so we've got this here. I've actually created an environment already, but if anyone doesn't know how to do it, I'm sure you do. Virtual env2. We're running Python 2.7 here, so not 3. Environment's created. We're all good. Activate your environment. So this is the environment that I'd already created. Bring down Pyramid. It's already installed, so we won't have any of these little networking issues that often happens. And pcreate -t, there's some templates that you can create in Python and Pyramid, sorry. I think there's 2 default ones, Starter and an SQL Alchemy one. And the directory you want to put it in. There you go, created. Have a look in here, and that's your basic web framework. So it's got everything that's in there so that it can answer a GET and serve a web page. Install all the things required for it, and then just pserve is a web server that comes with Pyramid. And it's running. If we go up here, there you go, web app running. Now, to get to that point, if you were doing it in C and C++, is a long time. It's a few days if you were doing it from scratch and hadn't done it before. Okay, and here's one we did earlier. And there is a basic login screen with authentication, basic authentication. We can log in. What's that, a minute? Go on, okay, no worries. Exciting. I was going to show you the code, but we don't have time. But it's about 20 lines of code. Of actual code that you have to write. Now, to do that in C and C++ is going to take you a good week or two, depending on who you are. So to finish up, web interfaces on embedded systems are awful. You can change it. The only way to change it is to convince your company, your developers, the people you buy off to do it. Python's a great way to work through that iterative process and get decent systems up. Profile your code and have fun developing. Thank you.
Very much.